Today we're going to look at the HackerRank question, swap nodes algo. So this question is quite wordy, but I'll try to simplify it. So first what this question does is define a binary tree. Okay, we kind of know that. And then it defines what in-order traversal is, where we traverse the left subtree, then look at the node in question or the root, then look at the right subtree. Okay. And then it talks about what swap-in is. So swap-in, subtrees of a node, means for a node, we swap its left and right children. So for example, if we're looking at node 1 and we're swapping its left subchild and its right subchild. So its left is 2, its right is 3, then we swap it so its left is 3 and right is 2. Okay. And then it says here, this is the crux of the question. So given a tree and an integer k, we need to swap the subtrees of all the nodes at each depth h. H is, I guess, the level or the height. So if h is a multiple of k, swap and the left and the right subtrees for that level. So for example, if we have k is equal to 1, we check if that level, this is one index by the way, if the level or h is a multiple of k, and if it is, then we swap its children, or the left subtree and the right subtree. So if k is 1, is 1 a multiple of 1? Yes. Then we swap 2 and 3. And then if this doesn't show it here, but since 2 is also a multiple of 1, for here, we would swap 5 and null, so 5 would be the left and null would be the right, and for 2 we would swap 4 and null, so 4 would be on the left and none would be on the right. And for 3, it is a multiple of 1, but they have no children, so it doesn't matter. Swapping them would give the same result anyway. Okay. Function description. Complete the swap nodes function and then to editor below. It should return a 2D array where each element is an array of integers representing the node indices of an in-order traversal after a swap operation. As the following parameters: indexes, an array of integers representing the index value of each node I, beginning with node 1, the first element as the root. Queries, an array of integers, each representing the k value. Okay, so this kind of sounds confusing, but basically we have an integer of k values, and for each k value, as we're looking at the levels, if it so happens that for a k value, it's a multiple of k, then we swap. And when we swap, we want to do an in-order traversal of that tree and put that in our result array. Okay, so what we have to do is iterate through the tree k times, and our result array would be of length k. And indexes here. Let's look at this parameter, indexes, an array of integers representing the index value of each node I. Okay, so what this basically means is, let's look at the sample inputs here. So this would be our indexes input parameter. So that would basically mean for one here, we have the left subchild of being 2 and right of being 3. And for the 2 node, the left subchild would be -1 and right subchild would be -1. And for the 3 node, left subchild would be -1 and right would be -1. Similarly here, you can see 1, left is 2, right is 3. For 2, left is -1, right is 4. for 3, left is -1, right is 5, and etc. Okay, and this is represented as a 2D array where each element is of length 2. I'll draw it out so it makes more sense. So these are the parameters, indexes and queries. So indexes would look like this. It would be an array, 2D array, with like 2, 3. This would be the nodes for, or the children for node 1. And then it would be -1, -1. And this would be a left and right subtree for node with the value 2. And then -1, -1, -1 represented none. These would be left and right subtrees for node of value 3, left and right. And queries, that parameter, it would also be an array of k values, so like 2, 5, whatever it may be. Okay. And so these are the only given inputs, right? So doing the swapping operation as I described would be much easier if all this were a tree. Because if we think about it, if we have a tree like 1, 2, 3, if we were to swap these two, it might look easy in an array, but we would have to swap these two to make sure 4 is still the left subchild of 2 and 6 is a right or left subchild of 3. And it's kind of hard to do that in an array here, so it'd be much easier to convert all of this into a tree. How would we convert it to a tree? Well, we can do it with a series of queues. So we will have one queue where it'd be like node, and it'd be like, well, these are the queues. So we'll have a node queue of the node we're looking at, and left children, and a right children. Okay, and left children would consist of the 0th index of each element in the index array. So it'd be like 2, -1, -1, and the right index would be the first index of each element in the indexes array. So it'd be like 3, -1, -1. And using the queue, what we would do is create a node here, and then pop it, or yeah, we would pop it. So okay, so we would have this guy here, and pop these first elements in the array, because this is a queue, so it's first in, first out. And to create left subchildren and the right subchild of these, and then put these back in this node queue. Put them here. Okay. And what we do is do the same thing, pop this node here. Yeah, these would be nodes. We would pop it here. And then for left and right queues, we would have -1, -1. Okay. And then that guy is done. And then we look at the next element in this node queue. It would be 3, and then these already popped, and then we pop these guys here, and then this left subchild would be -1, and the right would be -1. So that's how we'll build our tree. Okay. So first thing we want to do is in Python import a queue. And then define our tree building function. So root left children, right children. Okay. What we're gonna do here is create a node queue here, and first element in this node dq would be the root. And when we call this function, the root we're going to pass here is the node 1. And oh, I should probably define what a node is. Gotta build it from scratch. And this is how you build a node class in Python. Oops. Self.left because by default we'll have it none. Right, and by default we'll have that none too. Okay. So root here will be of type node. It'll be the node 1 will be passing in initially, and the first thing in this node queue would be root. So we're gonna traverse this kind of like a breadth first search way, except instead of searching for nodes, we're gonna build this tree level by level. Okay, so while when node queue is not equal to 0, what we're gonna do is well, I just remember in the function to pop node equals node queue dot pop. Yeah, we're just gonna pop. Okay. And the left child's value would be children.pop left, and right child's value would be right val equal to children.pop left. Also, we're getting the first element in each queue, first in, first out. So if left val is not equal to -1, meaning if it's not null, or it's not none, we're gonna create a node equals node left val, and node.left would equal to left node. And then finally what we're going to do is node queue dot append left node, and then we'll look at that after to build it, to create its left and right subtree from there. And we're going to do the same thing here, except for a right subtree. Node dot right is equal to right node, and then we're gonna append right node here. Okay, and then it's gonna iterate through that, and finally we're gonna return root value, which would be the one node, the node with value 1, and it's gonna be a built tree. Okay. Okay, in our main function here, swap nodes, what we're going to do is build this left children array and a right children array. First it's going to be empty, so what we're going to do is for I in indexes, left children, dot append I0. The 0th element is should be the left subtree's value. Okay, and same thing for right children here. Okay, and finally the root here should be build tree with node of value 1, and then passing in left children and right children, and then this should give us back the root node, and it should have the subtree built. Okay, so what's the next step here? Now that we have our tree built, so we could do a swap-in, I guess. We could build a swap-in. So what we're gonna do is, and how are we gonna know when to swap? So if we look at this example here, we have k equals 2 and k equals 4. So, and we have this tree here. Let's imagine this is the tree we just built. So we're going to look at k equals 2 first and check if there are any multiples of 2 for each level. So this is level 1, this is level 2. Great, so we're going to swap these and then continue down the levels, and this is level 4. It's a multiple of 2, great, so we swap these also. And the second guy here is the tree that we have right now. And then for this tree, we're going to look at k equals 4 and check if the level has a multiple of 4. It does in this level 4 here. So then we swap these. Swap their children, I mean. So that's pretty much how swapping is going to work. Okay. So pretty much for k in queries, we're going to do swap and pass in k and the root. And we got to remember, what do we want after we do the swap? We want the in-order traversal of the freshly swapped array after looking at it k. Okay, so we'll have our result array here. And we can just pass in this result array. Because in this swap function, once we do all this swapping, we're basically what we're gonna do, actually, we don't have to just put result in here. So we're gonna swap k and root, and then we're gonna do an in order traversal here, root and result, and then result. Actually, we're gonna do that, and temp result dot append temp result. Okay. Yeah, so for each k inquiries, what we're going to do is perform this swapping function for each level of k, on k, I mean. And then we're going to do an in-order traversal and store the results of those that in-order traversal of that tree in temp result, and then finally append temp result to this final result array. And finally, we're going to return result. Okay, so I guess we can work on this swapping function first. Okay, building this swap function here. What we can do, swap, we put in the k and the root. And basically what we're going to do here is another a breadth first search, where we go level by level, and if that level is a multiple of k, then we basically swap the left and right subchildren of that tree. So the level is going to equal to 1, and my breadth first search array is going to be root. So while length of BFS does not equal to 0, standard BFS, if level %k equal to 0, if it's a multiple, if that level is a multiple of k, then for each node in the BFS, we're gonna swap the left and right subchildren. The left and right children. So 10, and this is gonna be just a standard swapping. Dot right is equal to 10. Okay. Oops. Okay, so we're done that swap in there. And then what we're going to do is initialize new BFS. I'm going to put the next level in here. So for each node in BFS, if node.left does not equal to none, then new BFS.append node.left. And we're going to do the same thing for the right node. Finally, we're gonna assign BFS equal to new BFS and increment the level, so that in the next iteration we know that we're looking at the next level here. So that's pretty standard swap here. Okay, and then what we're gonna do after swapping that tree is do an in-order traversal on it, and then append that result from the in-order traversal to our result. So what we're going to do now is create this in-order array to get the result of the tree after the swap on this k. We're going to do it iteratively because there actually are a couple. Python has a limit on the recursion depth, and there is a couple of test cases that fail with the standard Python recursion depth. We can change the depth, but I'd rather do it iteratively just for some practice, I guess. So depth in order. I'm going to pass in the root and the array we're going to have a result put in. So for iteratively, you're going to have a stack here. And assign a current node to equal to root. So while current node is not equal to none, or len stack not equal to 0, so we want to continue traversing iteratively in this while loop as long as the current node is not none and stack is not empty. We're going to continue in this while loop. While current node is not equal to none, we're going to explore the left subtree first. And while we explore the left subtree, you want to remember this art place here, so we can look at it later to explore the right. Current node equals current node dot left. Okay. And then what we're going to do once we're done that is current node equals stack dot pop. And we're going to pop it here, and then we're going to append current node dot val, and finally current is for the right here. Okay, and that should be good enough here. Okay, so we have that. It seems like we're done here. Oops. Good thing that the IDE showed me that. So yeah, just to reiterate, we're gonna swap nodes. We're gonna build our tree here. We're gonna build our tree. Put the left children and right children in their own subarrays, in their own arrays, I mean, and then build a tree for there, starting at this root node of 1, and then initialize the empty result variable. And for each k in queries, we're going to do the swap. So basically in swap, if the level is a multiple of k, we swap. And then after we do that, for that tree that we just swapped for this level, for this k value, we're going to do an in-order traversal and append that result we get from that into our final result and return result. Okay. Yeah, looks good to me. Let's try running it just to check compilation error. Should be from. Let's see. So indexes, queries, type list, object is not callable. So swap node and so no, there should be a queue. And the left array and right array should be queues too. Let's try that. Let me see here, from collections, import DQ, that's right. Tree, here. Pen. Okay, there we go. Let's try submitting. And the test cases pass. I hope this made sense and helped you out. Thanks for watching. One thing I forgot to mention is the runtime here. So the runtime would be O of n times k, where n is the number of codes and k is the number of k inquiries. So basically we're gonna do the swap in, which takes O of n time, plus the in order traversal, which takes O of n time, which is 2n times the number of k inquiries. So it'd be 2n times k, but we're going to drop that constant, so it'll be n times k.